Hi there. We are on a 7th video on sequences and series today. So welcome back. I hope you've enjoyed or at least found useful the first 6. But here we are having to have a look at some other types of sequences and series. This time today we're going to have a look at what's called recurrence relations. Now a recurrence relation just means we're going to define the next term of a sequence based on the one that came previous. So we're defining one based on another term. So they're not too bad to get your head around, so I will explain how to do those, but you've guessed it, there's a few warm-up questions to have a go at before we get to the main meat of this lesson. So here they are, 4 to try. Pause the video now, or use the handout in front of you if you've got a handout of these notes, and try them on your own. When you're ready to see the solutions, press play, and then I'll guide you through how we arrive at the answers. Okay, so assuming you've just paused the video, now you're playing thinking, okay, let's have it. Let's have a look at the solution to warm-up question 1. So here we have a company that manufactures a headset. The company's annual profit can be modelled by this equation: P equals 70 minus 0.4 brackets x minus 24 all squared, where P is a profit in thousands of pounds and x is the selling price of the headset in just pounds. Sketch a graph of P against x, showing all intersections of the graph with the coordinate axes, giving answers to 2 decimal places where applicable, and give the coordinates of a turning point. Well, there's quite a few things to be doing here. So what we can see already is this equation is already in completed square form. Okay, and as well as that, we can see that the x squared term would be negative because the coefficient of this bracket is a minus 0.4. So what will happen is it will be a U-shaped quadratic. So it'll be a U-shaped curve, and the turning point we need to know will be when x is at this number turned with its sign switched, so opposite to minus 24 is plus 24, and the value of the maximum will be 70. So all I've done is I've got these values of 24 from this being a minus 24, I've just switched its sign, and the 70 is from the constant outside of the brackets. So we can label this in, and as I say, I can do that U shape. So it's going to be something like this. And that turning point, the maximum is going to be when x is 24 and p is 70. So I'll label this on like so. Okay, so that's that part done. The other part is working out these intersections of the axes. So this is where P is equal to 0. So to work these out, that one and this one, we just sub P equals 0. So x-intercepts, we just sub P as 0. And if we do that, what we'll get is the following. So we'll get 0 equals 70 minus 0.4 brackets x minus 24 squared. So I'm going to suggest we make this positive, so we can add 0.4 x minus 24 squared to both sides, which gives us 0.4 x minus 24 all squared, which equals 70. I can then divide both sides by 0.4. So I get x minus 24 all squared is 70 divided by 0.4. So let's try what this is. So 70 divided by 0.4. That's going to give us 175. We can now square root both sides. So we have x minus 24. Remember to plus or minus what we get when we square root this. So we can square root that answer, which gives us 5 root 7. So therefore, the x-intercepts, add 24 to both sides, will be 24 plus or minus 5 root 7. Now we need to give these to 2 decimal places where applicable. So what we need is to do this and then simply press the S arrow D button, the SAD button, this one here, to change it into a decimal. So first of all, I'll add 24 to it. Press S arrow D. 37.23. So in terms of pounds, that would be £37.23. And the lower intercept, 24 minus 5 root 7, we can work out very easily as well just by doing this. Press S arrow D, we get £10.77 to 2 decimal places. Remember, X is a selling price in pounds, and so 2 decimal places relates to the pennies, so £10.77. Part 2 of the warm-up will be interpreting this graph and interpreting in context question 1. And so we've got the curve, we've got the maximum labelled, we've got the x-axis intercepts, we're done, we're finished. We can now have a look at warm-up question 2. So it says, using question 1 or otherwise, explain why £40 wouldn't be a sensible selling price for the headset, state the maximum annual profit and the selling price of a headset that maximises the profit, and given that the company made an annual profit of at least £50,000, state, according to the model, the greatest possible selling price of the headset. So what we need to do, first of all, is remind ourselves of question 1. That's what we had from question 1. And just to, as well as that, remind you of the equation of this curve. The formula was P equals 70 minus 0.4 x minus 24 squared. So that is this curve here. So first of all, part A, explain why £40 wouldn't be a sensible selling price for this headset. Well, this here relates to £37.23. That relates to £10.77. So £40 would be down here somewhere. That would be £40. As you could see, this would be a negative profit. So in other words, they could sell it at £40. You can sell things whatever you want. It doesn't really matter if you don't care about going out of business. But if they sold it for £40, they'd be making a loss. So £40 would make a negative profit. Or you could just say £40 would be a loss. P is a negative value. i.e. it'd make a loss. B, state the maximum annual profit and the selling price of a headset that maximises this profit. That's just interpreting in context the maximum point. So the maximum point's here. So all we're doing is just interpreting that in context. So the maximum annual profit is 70,000. So £70,000. So profit max, P max, is £70,000. And the price of headset that maximises the profit is when we sell it at £24. That's when the selling price is 24 quid. And part C, given that the company made an annual profit of at least £50,000, state, according to the model, the greatest possible selling price of the headset. So this requires a bit more thought. So this company, it's saying here, made an annual profit of 50,000. Well, at least 50,000, I should say. So if 70 is there, we need to sort of guesstimate where a line at 50,000 would be. If 70 is there, 50,000 will be somewhere like this. So this is the line where P equals 50, as in 50,000. So the greatest possible selling price will relate to not this point here. That point would be the minimum selling price that would generate a profit of £50,000. This higher one would be the maximum selling price, which would generate a profit of £50,000. So we're looking at this point, in fact, because we're wanting the selling price, in particular, we're after working out this value down here. What is this value? So if I call this, I've not got any imagination tonight, I'm going to call that x. Okay. In fact, no, I won't. Apologies, because I've already got x in the equation. I'll just call that m for maximum. So P is 50. So 50,000 we can sub in P as being 50. So when P is 50, as in £50,000, that's going to be 70 minus 0.4 brackets of the x coordinate, which is m for maximum selling price, minus 24 all squared. A very similar rearrangement to question 1 now. So add 0.4 m minus 21, m minus 24, sorry, to both sides, gives us 0.4 m minus 24 squared plus 50 equals 70. Next, we can subtract 50 from both sides, so 0.4 brackets m minus 24 all squared. Take away 50 from 70, that gives us 20. Next, I can divide both sides by 0.4. If I do that, I get m minus 24 squared equals 20 divided by 0.4. That gives us exactly 50, in fact. So now if we square out both sides, so m minus 24 equals plus or minus the square root of 50. Now because we're after the maximum, we can actually therefore assume safely that we're just after the positive square root. So we can just go for the positive because we're after m being maximum. So therefore m will be 24 plus the square root of 50. So what does this come out as being? We get 24 plus 5 root 2. So as a decimal, so 2 decimal places, £31.07. £31.07p is the maximum it could have been sold for, with the profit still being at least £50,000. So that's question 2 done. Question 3. This is a modelling with differentiation question. So question 3, an open box is made from a rectangular piece of card measuring 64 centimetres by 24. Figure 1 shows how a square of side x centimetres is cut from each corner so that the box can be made by folding, as in figure 2. So this x here gets folded up and gets folded up that way, so we have it being x high. What we need to do here is show that the volume of the box V satisfies the equation V equals 4x cubed minus 176x squared plus 1536x. Okay, so what I need to realise here is the volume is the length, because it's a cuboid, it's length times width times height. Length times width times height. So in other words, it's going to be the length of the base, and then we're going to multiply by the width of the base, and then multiply by the height. So what we need to imagine happening here, with these corners cut away, these corners are going to be disappeared, so they're going to go. What's going to happen? I'll just illustrate this, in fact, because for the moment or two it takes, it might make it clearer for you. Those corners are going to be cut away like so. And the final one, same deal, can cut that one away. So the length of the base from one end to the other is going to be this. Okay, now initially the whole length was 64, but that's x and this is x as well, so what's left in the middle will just be 64 minus 2 lots of x. In a similar way, the width from this end to the top end, well, the full width was 24, but of course we're not including this, that was x, and this is x, And so what's left in the middle is 24 minus x minus another x, 24 minus 2x's. Then these sides are folded up. That's folded up and inwards. That's folded up. So these corners will meet. That corner meets that corner. That meets that one, and so on. And so what we've actually got here is that these sides, like so, and that one, now you have to at the bottom, these are making these sides here. Okay, so I'll just roughly do this because you might be thinking, how long is it going to take to colour it all in? I don't want to take too long to do this, despite the fact I'm a bit of a neat freak when it comes to these things. So these are making these sides essentially, and we're told, as you can see, that they have height x. So the height is going to be x. So subbing these things in, the volume, length times width times height, the length is 64 minus 2x. The width is 24 minus 2x. And the height is just x. So this looks like an awful thing to expand, but actually we can just pop this x inside of one of these first two brackets. So if I do that, leave this first bracket as it is. I'll leave it as 64 minus 2x. But if I just put this x on the inside, essentially I'm going to expand this out, but then re-bracket it. 24 times x is 24x. Minus 2x times an x is minus 2x squared. Now I can expand out using the standard GCSE methods. So first of all, 64 times 24x. I wouldn't do this without a calculator. So 64 times 24, that gives us 1536. So we've got 1536x. Then if I do 64 times minus 2x squared, that gives me minus 128x squared. Minus 2 times 24 is minus 48. So minus 2x times 24x gives minus 48x squared. Then finally, minus 2x times minus 2x. Well, minus times a minus gives me a plus. 2 times 2 is 4. And x times x squared gives me x cubed. And then if I neaten this up, you will therefore see that v equals 4x cubed. If I take away 128x squared, then take away another 48x squared, that gives me taking away 176x squared in total. And of course have this 1536x at the end to factor in. So we've proven what needed to be proved. We're now going to use this to answer warm-up question 4. So for the box in question 3, show that the stationary point of v occurs when 3x squared minus 88x plus 384 equals 0, and hence find the values of x for which v is stationary. So from question 3, what we had is the volume is 4x cubed minus 176x squared plus 1536x. So v is stationary when the derivative of v with respect to x is 0. So we need to do dv by dx and set it equal to 0. So if we do this, dv by dx, bring the power to the front and knock one off the power. That's the simple way of differentiating a polynomial. So 3 times 4 gives us 12. 1 less than 3 is 2, so we get 12x squared. This one here, bring the 2 to the front, That will give us minus 352. Can't hurt to double check. Yep, minus 352x. And if we differentiate just an x term, the x essentially just vanishes. So we can set that equal to 0. But this doesn't look like our target. But what you need to notice is, maybe I can divide everything through by 4. And in fact, that's exactly what we do. Divide both sides by 4. We then see that therefore, this divided by 4 is 3x squared. 352 divided by 4 gives you 88, so we have minus 88x. 1536 divided by 4 gives us 384. So that's what we needed to arrive at. So that's part A. And that's just from question 3, so you don't confuse 3 with 4. Part B, it says find to the nearest cubic centimetre the maximum volume of the box, and then it's saying show using calculus that this value is indeed a maximum. So it's going to be at a maximum when dv by dx equals 0. So it's going to be at a maximum, or a minimum for that matter, when dv by dx equals 0. So now we just solve this on the Classwiz. So 12x squared minus 352x plus 1536 equals 0. So if I Classwiz the heck out of this now, old school would be to complete the square or something like that. We get that x equals, well, let's see. I don't actually know. So if I move this to one side so you can see the screen properly, so that's a 12x squared. So we go menu, option A, mode 2, then 2 again. So type in 12 for the x squared term, type in minus 352 for the x term, and then the constant is positive 1536. Press equals and then equals again. One option we get is 24. The other option is 16 over 3. So either x is 24 or 16 over 3. So which one is it? Well, what we need to do now really is to just check. So is it both of these options? Is it just one? Is it none? So let's just check both. When x is 24, what happens? So for volume, when x is 24, will be 4 times 24 cubed minus 176 24 squared plus 1536 times 24. So what does that come out to be? Let's just see. So 4, oops, change the mode to normal mode. So 4 lots of 24 cubed minus 176 times 24 squared, then plus 1536 lots of 24. Press equals. We get a minus value, minus 9216. So the volume, when x is 24, is minus 9,000, roughly, cubic centimetres. Is that possible? Is that going to happen? Answer is no, this is a nonsense. And so when x is 24, we can't have that. And so x isn't going to be 24. So it must be when x is 16 over 3. So when x is 16 over 3, Vmax is going to be 4 times 16 over 3 cubed minus 176, 16 over 3 all squared plus 1536 times 16 over 3. So we can work out our maximum volume, and hopefully we should get a more reasonable answer. So I'm just going to switch for 24 for 16 over 3 in each instance. This time I'm not squaring 24, I'm just going to square 16 over 3. And here I'm going to be multiplying that by 16 over 3. Press equals. Awful looking number, but press SROD. 3792.5-ish. We say here to give it to the nearest cubic centimetre. So to the nearest cm cubed, it's going to be 3793. So 3793 cm cubed. Finally, using calculus, let's show that this is a maximum. So to prove it's a maximum, we take the second derivative. So we're going to do d squared v over dx squared. And what this means is we differentiate for a second time. So we're going to differentiate dv by dx. So 12x squared becomes 24x, minus 352x just becomes minus 352. 1536 vanishes. So because of that, the value of d squared v over dx squared evaluated when x is 16 over 3 is going to be 24 times 16 over 3 minus 352. So again, let's button bash and see what we get for this one. So 24 times 16 over 3 minus 352. That gives minus 224. Doesn't really matter what it gives us. All we're interested in is the sign. That's negative. If the second derivative is negative, that means the gradient is decreasing. And it's decreasing when it's at or just passing a maximum. So because the second derivative is negative, that shows that therefore v is a maximum when x is 16 over 3. So that's the warm-up done. We can now have a look at some recurrence relations. So let's introduce these, and then we can talk a bit more and try some worked examples like we always do. So, recurrence relations. What does this even mean? Well, a recurrence relation of the form u subscript n plus 1 has to be some function of a previous term. And if the next term is a function of a previous term, then it defines each term of a sequence in terms of a previous one. So, examples. So first of all, let's consider an arithmetic sequence. So I know that you probably know, in fact I know that you almost definitely know what the nth term of this one is, going back to GCSE. So in terms of a standard answer, the nth term un would be 3n plus 1, because it's going up in threes and it's 1 higher than 3 times table. But each number, comparing it to the one before, all it is we've got 3 more than the previous number. So un plus 1 equals un plus 3. And what we need as well to make us know a certain reference point, we need like an anchor to start us off. So normally you'll be given what u1 is, or maybe sometimes u2. So un plus 1 equals un plus 3. And we can say that u1 is 4. And that would be sufficient to generate the whole sequence. On the other hand, if it were geometric, like so, let's imagine this one. So each term as we move along, how does it compare to the previous one? So in terms of geometric sequences, what I'm thinking here is, what is the common ratio? So the magnitude of the numbers is increasing by 3, but it alternates between minus and plus. So actually, we're multiplying by minus 3. The common ratio is negative 3. So the next term is minus 3 multiplied by the one previous. un plus 1 equals minus 3 un, where u1 happens to be 2. So always important, we need to know a term at the very least, so we know where to start from which we can therefore build up. So that's the examples there. Let's have a look now at some meatier examples, exam type ones. So it says here, a sequence u1, u2, u3, u4, etc., is given by this recurrence relation. Un plus 1 equals 3un plus 2, and noticeably given u1, like I mentioned before. Find the value of u2, u3, u4, and u5. So what we can do here is just take this one step at a time. We're told that u1 is 2. Therefore, u1 plus 1, the next one, u2, will be 3 lots of u1 plus 2, which is 3 lots of 2, because u1 is 2, plus 2, that gives us 8. So u1 is 2, u2 is based off u1, which is 2, so u2 we now have is 8. So it's just iterative, it goes again and again. So now u3 is 3 lots of 1 before, which is 3 lots of u2, again with that plus 2. Because u2 was 8, that's going to be 3 lots of 8 plus 2. And 3 lots of 8 is 24, add 2. That now gives us 26. So again, u3 is based off u2, which was 8. We now can see that u3 is 26. u4, just go again, keep going. That's going to be 3 lots of u3 plus 2. Now u3 is 26, so that's going to be 3 lots of 26 plus 2. So 3 times 26, what's that going to be? You should find that it gives you 78. And 78 plus the 2 is what I meant to say, that's the 80. Check these off on a calculator, if need be. So that one's 80, because it's based off u3, which was 26. And finally, u5 is 3 lots of u4 plus 2. So it's going to be 3 lots of 80, because u4 was 80, plus 2. 3 times 80 is 240, plus 2, that gives us 242. So we've now calculated what u5 is. u5 is 242, and that was based off u4 being 80. So it just builds and builds and builds, and as you can see here, there is a clear pattern in terms of these numbers. So next, let's go and have a look at a second worked example. Slightly trickier, slightly more exam based. So, question 2, we've got again another sequence, A1, A2, A3, A4 and so on, defined as follows. So we're told that A1 equals 1, and the next one along, A n plus 1, is going to be the previous term, an, multiplied by p plus a to the n. P, we're told, is a non-zero constant. For part A, we have to find A2 in terms of P. So for part A, just using this here, we can say that A2 is going to be A1 P plus A1. However, we are told what A1 is. A1 is 1. So we can just sub this in. So A2 is going to be 1 lot of P plus 1, which of course is just P plus 1. Very simple start. So next, what do we have? For part B, we have to show what A3 is. When you show A3 as 1 plus 3P plus 2p squared. So for part B, using this idea here, A3 is based off A2. So it'd be A2 brackets P plus A2. But here, we now know what A2 is. A2 is P plus 1. So I can sub this in to work out what A3 will be in terms of P. So that's going to equal A2, that's P plus 1, then P plus A2, that's P plus 1. So very quickly I'm going to neaten this up. So P plus 1, P plus P is 2P, so 2P plus 1. Now we can expand this out fairly simply. So 1 times 1 gives us 1. I'm going to aim for it to be in the same form as what we're wanting to prove. 3p, well, 1 times 2p is 2p, and then p times 1 gives us an extra p. So we can see that it's going to be 3p, and the 2p squared is going to be p times 2p. So we get 2p squared, as we wanted to show. So that's not so bad, really. Part C, it says, given that A3 is 1, find the value of P. So for C, we know that A3 is this, so we'll need to just now sub formally that A3 equals 1. So A3, which is this, we're now told is 1. So if we just plug this in, so A3, which is 1, that must equal 1 plus 3p plus 2p squared. We can subtract 1 from both sides, which gives us 0 equals 3p plus 2p squared. I'm just going to move and give myself a bit more space over here. So like I was saying, this can factorise. I can factorise out of p on this side. So if I factorise out of p, I'm going to get 0 equals p brackets 3 plus 2p. Okay, so that's what I've got so far. And then I can say that because p is a non-zero constant, I can't have that being 0. The only way this can equal 0 overall is if 3 plus 2p equals 0. So therefore, 3 plus 2p equals 0. Solve that. So subtract 3 and divide by 2. P is minus 3 over 2, or if you want to, as a decimal, minus 1.5. Either is absolutely fine. Then for part D, you need to write down the value of this here. So 100, from r equals 1 up to r being 100, the sum of AR. Well, now we've got enough ingredients, we can actually work out what this sequence would look like. So A1 is 1, A2 we had was P plus 1, so if we just work this out here, that's going to be minus 1.5 plus 1. When A is 3, so A3 equals 1, and so that gives us a 1 as well. So what we can start to do is think about what this sequence would start looking like. If you notice here, 1 minus 1.5 plus 1, 1, it'd then go back to the start, it'd cycle. So what we have here is it's going to go 1 minus 0.5, 1. When you get to 1 again, if you shove 1 into here, then you'll get the same thing coming out again. So this is going to be a periodic sequence. I'll talk about what a periodic sequence is very, very shortly in this very video. So we're going to have a repeating block. Okay, so this block here is going to repeat. It's going to be 1 minus 0.5. Go back to 1 again, then it'll be minus 0.5. And the pattern will repeat. So we've got 100 terms. It means we're going to have 50 lots of 1 plus minus 0.5 when we're summing it. So therefore the sum of 100 terms means it's going to be 50 lots of this pair. So it's going to be 50 multiplied by 1 plus minus 0.5. And so 1 plus minus 0.5, that's going to be just 0.5, a half. 50 times a half, that's going to be 25. And so the sum of all those 100 terms would come out to 25. If you notice here, this pattern repeats, which seems strange, but this is actually one of the key components of today's video. So when it repeats, let's have a look at what these type of sequences are called. They're called periodic. So it starts over, repeats, repeats, repeats. Periodic is like cyclical. It goes in cycles. So a periodic sequence. It's periodic if the terms repeat in cycles. If the number of terms in the repeating block is the period of a sequence, and a sequence with period of n is typically written or stated as that the sequence is periodic of order n. So that one we just saw, where it was 1, then minus 0.5, then back to 1 again, that's periodic of order 2, because for 2 terms in the repeating block we're just 1, then minus 0.5. When it goes back to the start, it goes back to 1. So another example, if you had a sequence with nth term given by the nth term being minus 1 to the power n, when n is 1, minus 1 to the power 1 is minus 1. When n is 2, minus 1 squared is 1. When you square something, it always comes out positive. Minus 1 cubed, when n is 3, takes you back to minus 1. So you're going to switch from minus 1, positive 1, minus 1, again and again. This is periodic of order 2. It's order 2, this one, because repeating block is minus 1 plus 1. Then it goes back again to minus 1 plus 1. The repeating block is 2 terms in size. That's why you get periodic order 2. So here's an example of a periodic sequence. So we need to find the period of un. So a sequence, u1, u2, u3, u4, is defined as follows. I'm going to give you 2 terms here. The first term is 2, the second term is 4. un plus 1 equals the term immediately before un plus 1 divided by the term 2 terms before un plus 1. So this is a sequence, a recurrence relation, given in terms of 3 different terms. So I know u1 and u2, so I can actually write these down in terms of term numbers. So if I just write down term 1, term 2, term 3, term 4, 5, 6, 7, 8, hopefully I will have found the period by the time I get to the 8th term, but we don't know. I can write down the first term, u1 is 2, u2 is 4. So for part A, u3 would be un, so that's 1 less than n plus 1, so that's going to be u2 divided by u1. That's going to be 4 divided by 2, which is 2. So the third term is 2. I'll write about 1 in. Now u4 will be u3 divided by u2. The third term is 2. Second term is 4. 2 over 4, that's a half. So the fourth term is going to be 1/2. In fact, I'll get these in a different colour so they stand out a bit clearer. I'll put these in a blue colour. There we go. The fifth term, u to the u subscript 5, will be u4 divided by u3. The fourth term, as a half. The third term was 2. A half divided by 2, if I half a half, that's going to give me a quarter. So fifth term's a quarter. It's got no signs of repeating yet, which might seem a bit strange, but let's just carry on. U6 is U5 over U4. The fifth term is a quarter. Divide by U subscript 4, which is a half. A quarter divided by a half. This goes back to GCSE, dividing one fraction by another. You can do keep, flip, change, or if you want to, you can use your Classwiz. It's absolutely fine. If you want to use your Classwiz, I'd suggest actually doing that. So a quarter, I'm going to just write as 0.25. A half, I'm going to write as 0.5. I get a half. So the sixth term is a half. Still not gone back to 2 yet. The seventh term, U7, that's a bit high actually, I'll drop it down so it's not so close. That's going to be U6 divided by U to the 5. The sixth one is a half. The fifth one was a quarter. What's a half divided by a quarter? Well, hopefully, if you don't know keep, flip, change, you'll think of it like this. If you divide it by a quarter, it's the same as multiplying by 4. A half times 4 is 2. And finally, we're back to the beginning. We started there, we've got back to the beginning. So before it repeats, how many terms are in this repeating chain? I've got all of these terms here. 1, 2, 3, 4, 5, 6. Then it finally repeats and that 2 comes back on the scene. So the period is 6. So it's periodic of order 6. Because there's 6 terms in the repeating chain. So, keyword here is hence. Hence means we can use the previous part, A, to help us with this. So we're summing this sequence over 122 terms. So for part B, 122 terms, think of it in terms of this period. Period 6. So that's going to be, how many 6s fit into 122? So you can do this on a calculator if you want. So 122 divided by 6. Basically 20 point something, 20 and a bit left over. So I can chunk out this sequence, this summation, because I've got 20 and a bit, that's going to be 20 lots of the first 6 terms. 20 times 6 is 120, plus an extra 2 terms. So what it's going to be, the 20 lots of the 6 terms, it's going to be 20 lots of these here. So it's going to be that, those 6 numbers again, 6 numbers again, 6 numbers, 20 times. So after doing about 20 times, that'll be the 120th term. 121st is 2, 122nd, the final term will be 4. So it's 6 lots of the repeating chain, 2 plus 4 plus 2 plus a half plus a quarter plus an extra half. That's your first 120 terms. Sorry, times that by 20. My mistake. We're going to add on another 2 and 4. So once you've done that, we've done the whole question. So you can work this out first if you want to. Just add them up. 2 add 4 plus an extra 2. A half, I'm going to be lazy and just type 0.5. A quarter, again I'll be lazy and just type 0.25. A half, another 0.5. Get a 37 over 4. times that by 20, gives me this, then plus the extra 2 and plus the extra 4, that sums up to a grand total of 191. So it's about chunking out the sequence according to the period. That's the trick for those ones. Don't try and manually add up 191 lots of this, you'd just go crazy. Or probably both, you'd make a mistake and go crazy. So don't do that. Use the period as a hack into solving the question you're given. Final worked example now. Another sequence defined in this way next. K is a constant. We're told it's periodic of order 3. We're told that A1 is 1. We need to show that this relation holds true. K squared plus K minus 2 is 0. So let's try from the top. Let's try working out part A. A1 is 1. So A2 is going to be 2K divided by A1 minus K. But we were told that A1 is 1, so we can just substitute this in. If A1 is 1, then 2K over A1, that's just going to be 2K divided by 1. That's just 2K. So 2K minus K gives us K. So know what A2 is. A2 is K. Next, we can generate A3 based on A2. So A3 is going to be 2K divided by A2 minus K. And that's going to be 2K divided by K this time, because A2 is K, minus K. So if we do that, the K's are going to cancel on the top and bottom. And that'll just give me 2 minus K. So A3 is 2 minus K. You might be thinking, well, where's he going with this? Where am I going with this? Well, we can use this idea that the sequence is periodic of order 3. So based off that, the first term, A1, we're told is 1. A1 is 1. A2 is K. A3 is 2 minus K. If you notice, very obviously, this is 3 terms, which is the same as the period. This means, after these 3 terms, the cycle will repeat. So I know, therefore, that we need to go back to 1 after this. So 1 must be A4, and that's the way into it. So just bear in mind that A4 is 1. So A4, again, same idea, 2K divided off 1 before it, which in this case is A3 minus K. But 2K, A3 is 2 minus K, then all of that minus K. I know that has to be 1, based on what I said earlier. A4 has to go back to 1. So now what we can do is we can solve this equation to prove this relation. Well, not solve, but rearrange it anyway. So if I multiply everything by 2 minus K on both sides, 2K will become, so 2K over 2 minus K will just give us 2K, times a minus K by 2 minus K as well. Then 1 times 2 minus K is just 2 minus K. Now again, I'll just shimmy over to the other side to give myself a bit more space and carry on. So if we expand this out now, so 2K minus K times 2, that's minus 2K. And then minus K times minus K is plus K squared. That gives me 2 minus K. 2k minus 2k, that'll cancel. Get all this to the other side, so minus 2 and add k. I can therefore see that k squared plus k minus 2 equals 0, which we wanted to prove in the first place. So that's proven the result we needed. Part B, we're told that A1 is not equal to A2. So we now need to evaluate the sum of the first 50 terms from 1 to 50, from the first to 50th. So here we now know what k has to be based on this quadratic. So if we factorise or solve, you can Classwiz it if you want to. Doesn't matter which way you go around it. Two numbers that multiply to minus 2 add up to positive 1. That's going to be a positive 2 and negative 1. So therefore, we can say that either k is minus 2 or k equals 1. Now, we were just told that A1 can't equal A2. If k did equal 1, then this sequence here, 1, k, 2 minus k and 1, the second term would be 1 because k is 1. So actually we have to reject this idea that k can be 1, because if it were, the second term would be 1, which isn't allowed. So therefore, we've got that k equals 2. Sorry, minus 2. I can't read my own writing. Terrible. So now the sequence one k 2 minus k cycles back to 1 again. We can now sub in k being equal to minus 2. So if k is minus 2, we can actually work out actual numbers, what the sequence is. So sub that k is negative 2. First term is obviously 1. Second term k, that's going to give us minus 2. 2 minus k, 2 minus minus 2, that's going to give us 4. We'll go back to 1 again. That's going to cycle and cycle and cycle. So we need the first 50 terms. So this repeating block, the first 3, well, how many 3s can I fit into 50? That's going to be 16. So the sum from 50 to 1 of AR is going to be 16 lots of 1 plus minus 2 plus 4. 16 lots of the first 3, and then I'll have another 2 after. So the 49th term will go back to 1, and the 50th term will be minus 2. So the final step is to sum those. So I've got 16 lots of 1 plus minus 2 if you want to. We can just put 1 minus 2, same thing. Plus 4, then plus 1, plus minus 2. So I'm going to minus 2 off like so. I then get 47. Again, using the period as a hack to try and find out how to section out the sequence, and then if it runs over, you just fill in the extra bits with the first few terms, as many as needed. That's all from me. Now, you know what to do. You need to try some of these on your own, don't you? So, these are the suggested exercises. So, page 80, 3G, is an introduction to recurrence relations. Try these questions from 3G. Then 3H is about the periodic sequences which we mentioned. So, from 3H, then try questions 2, 3, 4, and 5. Check your work regularly, self-mark using the back of the book to see if your answers are correct. If not, check with your neighbour. If you're still not sure, please do ask me. Come and find me, or send me an email, or even contact me on this page. I do not really mind, but in person is probably better. Please do like and subscribe. That is always very appreciated. I hope you found this useful, even if only a bit of a video, not the whole thing. I don't ever expect you to watch a full hour of me. That would probably bore you a bit too much, but if you do, that's absolutely great. I'll stop prattling on. I'll close down now. I'm going to say goodbye and have a nice day until next time. Ciao for now.